All right, so in class today we learned about Rydberg's equation, which allows us to predict the emission wavelength with a certain transition within an atom. We learned that Rydberg's constant has a value of 2.179 times 10 to the minus 18 joules. We also learned that the energy change associated with the transition, which by the way we know is equal to hc over lambda, is also equal to Rydberg's constant times 1 over the final value of n squared minus 1 over the initial value of n squared. And we did a problem in class today. I would like to rework that problem for you and lead you to the 3 that I want you to work on for your homework tonight. So in class, we looked at a transition from n equals 6 to n equals 2. So my original n is 6 and my final n is 2. Those values are going to be plugged into the equation with the corresponding arrows, and Rydberg's constant will be plugged in where I've just drawn the arrow. So what I want to do now is go to a blank slide. So delta E equals Rydberg's constant, which is 2.179 times 10 to the minus 18 joules. And that's going to be 1 over 2 squared minus 1 over 6 squared, which is going to be 1/4 minus 1 over 36, which is 9 over 36, minus 1 over 36, which is 8 over 36. And I'm going to multiply this by 2.179 times 10 to the minus 18 joules. Notice there's no unit in the parentheses, and we know that energy has a unit of joule, so a change in energy should also have a unit of joule. So I'm simply going to plug these values into my calculator. And I obtain an answer of 4.842 times 10 to the minus 19 joules. Now this isn't my final answer, but I'm going to box it in because it is an essential part of the answer. So we know that 4.842 times 10 to the minus 19 joules is equal to hc over lambda, which of course is equal to delta E. I can rearrange these variables and get an expression for lambda, which will be hc over delta E. I do this by multiplying both sides of the equations by lambda and dividing both sides of the equation by delta E. At this point, I can plug in values, and I would not plug in values until you're at this point in the problem. So we know 6.63, which is Planck's constant, times 10 to the minus 34 joules times seconds times 3 times 10 to the 8th meters per second divided by 4.842 times 10 to the minus 19 joules. If I take a look at my units, joules will cancel, seconds will cancel, which leaves a unit of meters, which is the unit of wavelength. So now I simply have to plug this into my calculator. Remember to use parentheses if you have a TI. And when I do this, I get an answer of 4.108 times 10 to the minus 7 meters, which is 410.8 nanometers. Either of those answers are fine. I would report it in nanometers, a little bit easier to handle. And if we go back and look at the spectrum, (410.8) correlates nicely to this emitted wavelength. So mathematically, we have justified the existence of this emission wavelength that is right around 409 to 411 nanometers. And we've computed this with an error that's less than 0.5%. So what I would like for you guys to do for homework is to compute these wavelengths for the transition of n equals 5 to n equals 2, n equals 4 to n equals 2, and n equals 3 to n equals 2.